Great. So perhaps I'll just start by introducing you. It's such a pleasure to have Michelle Girvan with us today. She's a very prominent researcher in network science. She was trained as a physicist and then completed her PhD on the structure and dynamics of complex networks under Steve Strogatz at Cornell. And then she carried out some postdoctoral research at Santa Fe Institute and later joined the University of Maryland, where she is a professor today. I think the Girvan-Newman algorithm for community detection was one of the first things I looked at when I got interested in network science almost 25 years ago. So Michelle's name has been sort of etched in my mind ever since. And I'm sure the same is true for several others in the audience today. Uh, Beyond her research, Michelle has played an important role in building the field itself, and that includes her current leadership of the Network Science Society. And yeah, of course, many other accolades and titles. But Michelle, we're so delighted to have you with us today, and we look forward to your talk. Over to you.
Great, thank you. And you can see my slides, okay?
Sorry, that was a yes. Yeah.
Okay, great. All right, I am delighted to be here. I'm going to talk to you today about some work our group has been doing for the past few years. And I understand this is a pretty broad audience, a lot of representation from network neuroscience, some other network science components. So I'll try to keep this pretty broad and try to highlight the parts that I think might be most interesting for you guys to think about. So my talk today is on this notion of from externally tuned to internally adaptive. We think about brain-inspired mechanisms for robust reservoir computing. So reservoir computing is a kind of machine learning architecture that I'm going to tell you more about today. Oh, no, my controls aren't working right. Okay, there we go. So the area that I work in general is machine learning meets network science. And I think of this as having two umbrellas. We can ask ourselves, how can machine learning help us understand complex networks? So in network science, we explore how interaction patterns give rise to system behaviors. And machine learning can help us identify patterns that are prevalent in different scenarios, patterns that maybe we didn't hypothesize a priori. It can also help us predict the dynamics of complex networks, for instance, looking at brain network dynamics. And that's an area where I've worked on machine learning schemes for predicting dynamics of complex networks. But we can also think of the flip side. Which is how can network science improve machine learning? So, machine learning approaches, including the kinds that are large language models really transforming AI today, leverage artificial neural networks. And understanding the interplay between structure and dynamics in these systems can help us advance machine learning capabilities. So, the motivation for the specific work that I want to talk about today is that modern AI and deep learning models achieve really impressive performance by optimizing huge collections of internal parameters. But this has a downside. It can require substantial computational and data resources. So we work on a kind of machine learning scheme called reservoir computers that keeps the internal dynamical connections fixed, and it trains only an output layer. But there's some caveats, so it still requires careful choices for reservoir design. We're inspired by biological neural networks that use plasticity mechanisms to maintain stable activity and operate in a region of strong information processing capability. So the ideas here that we think about is, can we use biological mechanisms to inspire our reservoir computers to be more robust? So what is reservoir computing? I imagine that many of you are not so familiar with reservoir computing, so I want to give you a brief overview comparing it to deep learning, which is a foundational layer in modern AI. So in deep learning, what happens is information is processed through layers of neuron-like units, right? So for a classification task, I give it images like dogs, cats, etc. I feed this image through this network, and the network is trained to output the correct classification. The deeper layers, so the weights between the neurons in each layer are trained via large scale parameter optimization that involves back propagation, but I'm not going to tell you the details about that today. The idea is that these deeper layers perform higher level information processing. So the first layer is just maybe about pixels, the second layer about edges, etc. And these are really powerful. And they're very good for classification tasks, but they're computation and data intensive. So by contrast, if we think about reservoir computing, which was introduced in the early 2000s independently by Jaeger and Moss, we feed our input into this high dimensional system with recurrent links called the reservoir. And so only these output weights are trained instead of training all the connections between the links. And so this means that it makes training very simple, and it's also quite amenable to simple hardware implementation. So there's interesting research recently on, well, are these very low energy solutions to computational problems as compared with modern AI, which, as many of you are probably aware, is very energy intensive. And so the thing that I like about the reservoir computing side of things is it allows us to probe the network properties that support computation across tasks. And that's the general part of this that I've been interested coming at this as a network scientist. Now, primarily, our group has thought about using reservoir computing for time series prediction. And this is a common application for reservoir computing. So we feed an input time series U of t into the reservoir, and we predict the output at time t plus delta t. And so, for instance, we can imagine, let's say we're feeding EEG data from the brain and trying to predict the future EEG data. We do that in one of our projects. So the main component here is this reservoir has these neuron-like units. They have random sparse connections and internal firing dynamics, and we also get the input that gets fed into the reservoir, that the reservoir dynamics are determined whereby the state of one of these neuron-like units at time t plus delta t depends on the states of its input nodes through the adjacency matrix A, plus the external input that it gets from this signal U of t, which can be a vector quantity. And it's these feedback loops or this recurrence inside the reservoir network that provide the system memory, which means that the state of the reservoir at any given time depends on the history of past inputs. And as I said before, training is elegant in this kind of system because we're only training these output weights. We train them via linear regression with ridge regression with some regularization to prevent overfitting. But the basic idea is that we train the output weights to give a good prediction for the next time step. And it's simple because we're not training that input part, rather we're leveraging the complexity of this. Now, for those network scientists out there, you might be thinking, oh, how does the structure of this internal connectivity matter? And it does matter, and that's actually how I came to this problem maybe 10 years ago, thinking, oh, as a network scientist, we can think about these different types of ways of wiring up the reservoir network. But in fact, what was surprising to me was that it wasn't as sensitive to the internal structure of connections that then as I expected. But there's still some open questions there. Now, okay, so if it's not as sensitive to some of the network features, what are the important features of this generic reservoir where I feed in a time series, I train it to predict the next time step over all the training data, and then I can run this autonomous mode to predict not only one time step out, but multiple time steps out. So what I do is I take the output, I feed it back as input, and I run this as an autonomous dynamical system that is designed to mimic the system that we were observing. So the reservoir computer requirements are that I have an input-output system. And the generic reservoir, the basic idea is that it's going to project this relatively low dimensional input time series. Let's say you can think about these EEG traces along different channels into a higher dimensional space. And then when I'm in that higher dimensional space, things are more linearly separable. But the important part here is that the reservoir gives me a complex repository of dynamics. So different inputs give different outputs. It has a large dynamic range. And so when I train these outputs, it gives me what you might think of as a universal dynamical system with the training. And the internal memory is an important part of it, that the state of the reservoir at a specific time depends on the previous states of the inputs. It encodes information about what had been happening in those time series. So we've worked a lot on reservoir computers by our team at the University of Maryland, mostly on complex time series prediction tasks. But today I want to talk to you a little bit more about some brain-inspired modifications to reservoir computing. So before I go into this, you may be more familiar with some other machine learning approaches. So I want to place reservoir computers in the machine learning landscape. So on the right here, I have these low dimensional statistical models that are really interpretable, but not as powerful. And then on the left here, I have these flexible data hungry models that are highly expressive and powerful, but really hard to interpret. So we say these systems on the right have what we call high inductive bias. We're making assumptions, like, for instance, we can make assumptions about the different terms that might be that might be included in my dynamical equations that underlie the process that I'm observing. I don't make any assumptions in these data hungry models. So these are things like deep learning, LSTMs, GRUs. If you don't know about that, don't worry about it, or deep recurrent neural networks, and then modern transformer models, which underlie large language models. And the idea is they're trying to learn complex behavior from large data sets. These high inductive bias models, they might be informed by physical principles of the underlying equations, and they combine linear and explicit nonlinear features or structural assumptions. Reservoir computers fit somewhere in between. We don't make quite as strong assumptions as in the high inductive bias case, but it's also not quite as interpretable. However, they're still a lot more interpretable than these data-hungry models and much more efficient. And so we feel it gives us a nice in-between to really have more power, but also give us more interpretability. We can get further, the reservoir computer, it's this complex network. And sometimes it's hard to interpret what's going on in that case. we can actually combine methods of reservoir computing with some of these lower dimensional models to improve things even further. And one of my motivations in this is, for example, in network science, many of you are network scientists. Sometimes we see very expressive network models used in cases where something simpler would be sufficient to answer the question that's being addressed. I mean, I think network approaches are fantastic and very applicable in many cases, but I do think sometimes they're used when they're not needed. And so similarly, these forecasting tasks also vary widely in the complexity that they actually need. And this is true, I'm sure you've experienced if you play around with ChatGPT or Claude or things like that. If you're doing it for scientific computation tasks, a lot of times you're throwing a lot of processing at a problem that needs, that can be better handled with a lower complexity solution. So if we hybridize the flexible reservoir computer with some of these less flexible but highly interpretable models, that gives us simplicity where possible, and they're expressive when necessary. It also gives us a little more interpretation on the combination. So what we did in this is, I have my reservoir network down in the bottom at blue as I had before, but I also have this simpler non-linear vector autoregressive model. So what that means is I take my time series U of t, I have time delayed observations of that, and in this gold vector autoregressive model, which is also called next generation reservoir computing. What I'm doing here is taking linear and nonlinear combinations of these time delay components. And then I'm also feeding that signal through the reservoir, and I train all of these output weights in red here to predict the next step. So the goal here is we want to achieve the performance and flexibility of this lovely reservoir computing model while preserving some of the efficiency advantages of the NGRC and also some of the interpretability. Because I can look at, okay, I have this time series U of t, and if I look at what combinations of these time delays and the nonlinear combinations get the most weight, then I can understand more about the underlying process than I can by looking at this complex reservoir output weights for the individual nodes. So just a illustration of forecasting the Lorentz system, which is a chaotic system. So the true Lorentz system has this butterfly attractor that many of you will be familiar with. And because it's chaotic, it can be hard to predict. Reservoir computers are really good at predicting these, but you need a large enough reservoir. Here, we've made the reservoir very small in terms of the number of nodes. I don't remember the actual number here, but I think it was as small as 50. You can do really well with a reservoir of 200. So here's a weak, small reservoir that can't predict it. And a weak NGRC, so the simpler nonlinear vector autoregressive model. The NGRC can't handle the Lorentz model when the time step is large. So the NGRC really works well if your approximation of linear and nonlinear combinations of the input data makes sense, and that usually happens only at very small time steps. But we show here we can take a very too small RC plus a not so good NGRC in gold, and the weak RC in blue. And here I'm looking at the power spectra. So I'm getting a sense of the true dynamics of the system. The true system is in black. The hybrid system is in red and is a great match. So what we find is this hybridization is robust to large time steps and changes in the reservoir construction. and basically weaknesses in either component alone. So we're effectively combining the idea of the flexibility of our reservoir with so we're combining the implicit dynamical richness of the reservoir with the NGRC's structured linear, nonlinear feature sets. Basic takeaway, this is going to reduce the dependence on the extensive parameter tuning of the reservoir and improves general robustness and lowers computational costs. So what we just saw was that this hybridization, well, what I just told you, I didn't actually show you extensively, is that these hybrid models reduce sensitivity to how we choose the dynamical reservoir hyperparameters, dynamical and structural. But can we go further by improving the reservoir's internal dynamics? And there, we're going to go back to some of these brain-inspired features and investigate the role of excitatory inhibitory EI balance. And this work is in collaboration with Keshav Srinivasan, who's a former graduate student who was co-advised by Dietmar Plenz of the NIH and myself. So our motivation started with thinking about the advantages of criticality in neural networks. So experimental studies suggest that many biological networks may operate near a critical boundary or phase transition, as you see in this figure here, where activity dies out and where it gets amplified. So I'm a physicist, so I like to think of this as an order parameter versus tuning parameter plot, where I'm looking at something like maybe the average firing rate as a function of some parameter that controls the network structure or maybe the dynamical rules, and I see a phase transition. Close to this critical point, we expect to see a power law distribution of avalanche sizes. And so avalanche size is the number of firings following an initial triggering, with that exponent given by the theory of critical branching processes. The idea here is that proximity to this critical point gives information processing advantages like maximum dynamical range, which is the range of stimuli over which the system can differentiate responses. I've done some previous modeling work with collaborators that suggests that certain network architectures can display critical-like dynamics, so the advantages of these power law distributions, even when you're quite far from the critical point. So that's what we kind of came in. So that has the advantage of not having the fragility of potentially crossing over the critical boundary, but still getting the power law distributions that we want. So here, we want to explore how the balance between excitation and inhibition influences the reservoir's dynamics and performance. So here what I have is a somewhat slightly modified reservoir update equation. So I have my state of my reservoir nodes at time t plus delta t is a function. So the state of a given node depends on the nodes in the network that give it input, and the external input that comes over here through the input layer minus some threshold. So it's this sigmoid firing function. But what I've done here is explicitly said, okay, well, some of my edges are excitatory and some of them are inhibitory. And I'm specifically going to think about this balance between excitation and inhibition. So I can think of the local balance for a node is the sum of its incoming excitatory links minus the sum of its incoming inhibitory links. And the global balance is just the sum over all nodes of the local balance of each node. Now, there's lots of ways I can set up this network. I can vary properties of the input matrix. I can vary different features of the adjacency matrix. As network scientists, you can think there's lots of features in there that I can vary. So there's lots of hyperparameters involved in setting up the reservoir. And one of the challenges that really gets swept under the rug when I see talks about reservoir computing is like, oh yes, this performs great on this task, but usually there's some hidden hyperparameter tuning to get the reservoir to a regime that performs well. So there's different approaches to setting up the reservoir, some background. Nice paper by Eric Bolt on explaining the surprising success of reservoir computing. This notion of do reservoir computers work best at the edge of chaos has been discussed before. And some good guidelines about how to set up the network for the reservoir, but a lot of open questions. So first, let's think a little bit about what happens when we vary the level of inhibition in the system. So our setup is that we have a constant number of nodes and links. We look at different fractions of inhibitory nodes. Here, I have inhibitory links and excitatory links having equal strength. In the brain, the inhibitory links are on average about 4 times stronger than the excitatory links, but there's proportionately fewer of them, so we do observe something close to a global balance. My links here are adhering to Dale's law, which is that excitatory nodes have outgoing excitatory links. So our nodes fall into 2 different categories, and then all of the outgoing links are of a certain kind, excitatory or inhibitory as appropriate. So what I'm doing here is I'm showing you as I go across the columns what happens if I go from purely excitatory to increasing the amount of inhibition. In green, my green column is the balance case, and my final column is this 80% inhibition. Now, if I take this case where everything is excitatory, and what I'm looking at is the average firing rate in my network as I'm feeding in this input. I'm varying just 2 hyperparameters here, a reservoir link scaling hyperparameter and my firing threshold. What I see here is the network in almost all of this hyperparameter space has very boring behavior. Either all the neurons are silent or they're all saturated, firing all the time. And there's this narrow region where something interesting happens. And in this narrow region, on the bottom row here, I'm showing you a performance metric. This is the memory capacity of this network, and it's only going to be good in this bottom region. So if all the links are excitatory, I have good performance only near this phase transition. But as I increase the level of inhibition, I see this region of good performance, purple, over a much broader region of performance. And it's not necessarily just close to this boundary. And in fact, what we often see is in the inhibition-dominated regime, I have this larger region of purple. So even better performance in some cases in the inhibition-dominated regime. So that led us to want to explicitly vary the balance of excitation and inhibition. So our setup in this case is varying the EI balance by adjusting this mean strength of inhibitory links, keeping all the other parameters fixed. And remember, my local balance for a node on my reservoir network is the sum of its excitatory links minus inhibitory links. My global balance is the average over all the local balance values. The silent is where, oh, this would be average firing rate less than 0.05. That's a typo there. Saturated in this plot is the average firing rate greater than 0.95. And this oscillatory synchronized region is where I have coherent oscillations that are neither saturated nor silent, and the coherence is greater than 0.9. So I get in this phase space where my threshold is one of the hyperparameters I'm varying. My other hyperparameter is this global balance. I get, if I look at the firing rate, I have those regions, this silent region where nothing's happening, a saturated region where everything is firing all the time, an oscillatory region where everything's in sync, but it has very little information processing capabilities, and this region in between where there can be different responses. And if I can think about this by looking at the mean neuronal entropy in this system, which I'm indicating here, darker regions have higher entropy. And the memory capacity is a task that I'm testing on, saying, okay, well, here, how good are these systems at a memory task? And we see the best performance in this intermediate regime. So the best performance occurs, and if I look at where that happens as a function of the global balance, we see that the best performance occurs when the network tends to be either balanced or over-inhibited with firing rates that are in this middle range, but that don't get us to this oscillatory synchronized state. So when we saw this, we thought, okay, some kind of local balance mechanism may be appropriate here. What if we allow the input strengths to self-adapt towards some level of local balance? So in my excitatory inhibitory reservoir, each node gets designated as an excitatory neuron or an inhibitory neuron, and all its outgoing links are the same type. So excitatory neurons have excitatory outgoing links, inhibitory have neurons have inhibitory outgoing links. And now what we look at is the local firing mechanism. So each neuron has a target firing rate, and that color is indicated by the outside of the circle. And it has a true time-dependent firing rate that you see as the color of the inside of the circle. If the neuron fires more than its target weight, what we do is we increase the inhibitory connections, incoming inhibitory connections. So we increase this connection here, which brings this neuron down to closer to its target firing rate. So its incoming inhibitory weights are raised by a small amount if it's firing more than its target rate, and if the opposite occurs, the weights are lowered by a small amount. So I get this adaptive network. And so I adapt the network. What I'm doing is I'm feeding the input in, letting the network adapt so that the firing rates are in a range that I kind of want it to occur. I don't get too much that gets saturated or silenced. And so if the target firing rate is low, moderate to moderate, this should lead to a configuration of good performance because I'm I'm adjusting these input weights so that the network is in a good performing regime. And notice this is not the same as training the internal network because I am adjusting it slowly and generically and not training much of the details of the network. And I'll say a little bit more about that later. And as I said, here we have this two-step training process. We first feed the input through once and allow the links to adapt. And this is a very computationally inexpensive process. And then we feed the input through again and train the output weights. So let's look at what happens with the mean local balance as a function of adaptation, starting from different levels of initial mean local balance or global balance. And so here, what we're doing is we're training these neurons all to go to their target firing rate of 0.5. And so we get target firing rate of 0.5 gives us a mean local balance or a global balance of 0. Wherever we start out, we get to closer to this globally balanced state. And if we look at our memory capacity, which is one kind of measure of performance in these networks, as a function of our adaptation time steps, what we see is we get this much improved memory capacity regardless of where we start from. We see that the over-inhibited networks, globally inhibited networks, started out with better memory capacity than the neutral network in gold here. But even the one that was globally neutral to start, because the local balance of all the neurons is going towards 0, that's what's improving its memory capacity performance. So even starting with globally balanced is not enough. It's this plasticity mechanism that improves the local balance. And so after adaptation for local balance, the performance is substantially improved. But, one thing I've done here is I've introduced another hyperparameter in this system. I have this target firing rate. So how does performance depend on this choice of target firing rate? So what I do is I compare my non-adaptive network, and I'm taking two hyperparameters, the input scaling and the global balance, and I'm optimizing those for each task. And the other hyperparameters are set at default values. And what I have here is that in my adaptive network, the input scaling is task optimized. The target firing rate is the same for all the neurons, and the other hyperparameters are set at the defaults. So I've considered a few different, so I've these three here, NARMA 10, Mackey Glass, Lorenz, are time series prediction tasks. I'm varying my target firing rate. I'm showing you performance as a function of target firing rate. And this baseline is in the optimized non-adaptive network, so where I've tuned the hyperparameters. And we see that this adaptive network outperforms the baseline quite substantially in many of these cases, in all the cases, but in some cases more substantially than others. But the best performing adaptive networks also require optimization of two hyperparameters, the input scaling and the target firing rate. So the question is, can we reduce the number of hyperparameters we optimize by making these target firing rates heterogeneous? Again, drawing from some ideas from the brain. So instead of making these target firing rates identical for all neurons and then tuning that as a hyperparameter, what we do is we consider a distribution of target firing rates with mean 0.5 and standard deviation 0.2. The idea is we want to stay away from target firing rates that are too close to 0 or 1, saturated or silent, because those are not informative. Those are not responsive neurons, but we want to have a range of responsiveness of our neurons. So I look again across my 4 different tasks and I compare what's my best performing non-adaptive case where I've tuned 3 hyperparameters. My best performing homogeneous adaptive case, that was what I showed you on the previous slide, where I tuned the input scaling and the target firing rate, which is identical for all neurons. And then finally, in green stripe, this heterogeneous adaptive, where I just give it a distribution of target firing rates and I tune just that input scaling. So I see that the heterogeneous adaptive networks are offering similar performance as the best performing homogeneous networks where I tune that target firing rate for the task. And that gives me one fewer tuning parameter and more robustness in these systems to different types of scenarios. One thing that I'll note here is I'm comparing these three different types and looking at the neuronal properties. So here in column A are my non-adapted reservoir computers where the hyperparameters have been tuned, my homogeneous adaptive where I've tuned two hyperparameters, and my heterogeneous adaptive where I've tuned just one hyperparameter. And so in my non-adaptive RCs, my horizontal axis is the firing rate. And I'm looking at in the first column, the local balance parameter, and the second, the neuron entropy, and these output weights, how much that neuron gets weighted in terms of making predictions or in terms of completing the task. And what happens here, if we look at this firing rate, let's look at this neuronal entropy. The firing rates that are near 0 or near 1, these neurons have very low neuronal entropy and don't contribute in a positive way to our calculation, to our information processing. So the homogeneous, what we've basically done is removed these low entropy nodes. And in our head, but everything is firing at the same rate, essentially, or very close to the same rate. There are important fluctuations that give us more information, give us the information processing capability, but they're quite small. In our heterogeneous adaptive, we get the benefits of kind of cutting off this lower neuronal entropy. So we have no low entropy neurons, but still a range of dynamical behaviors that is good for a range of tasks instead of being task specific, which is what happens more in the second column here, where I've tuned the target firing rate for the task. Now, one thing I want to mention here is what we did here is I took an initial reservoir and I said, okay, I want to tune these excitatory and inhibitory links such that I get better performance. And I did it with these slow adaptations. But in fact, we don't need to do these slow adaptations. We can also just start with a random matrix or these random excitatory and inhibitory adjacency matrices, and then just do a rescaling of our inhibitory links in just one step. And so what I'm showing you here in orange are the one-step adaptive RC, where these are homogeneous. They all have the same target rate. And in orange striped is the heterogeneous, where I give the network a distribution of target firing rates. And we see that the adaptive networks with local balance, whether it's the slow adaptations from green or the one step in orange, they significantly outperform the non-adaptive networks, and that the one step rescaling is almost identical to the multi-step, the slow rescaling. So I can just have designed it that way, even though what we did here was motivated by these plasticity mechanisms that are explored in other brain models. So, summary of what I've talked about here, we have flexible, we're thinking about this spectrum of flexible data hungry on one end to these low dimensional statistical models. And the paradigm that I've been talking about, reservoir computing, sits in between, which gives us a lot of advantages with the rich network dynamics we can access, but also the lightweight training. I talked about where we can hybridize these RC models with NGRC models, which are a type of these low dimensional statistical models, which unites the complexity of network dynamics with the low dimensional statistical structure advantages of even more interpretability, and it gives us more robust behavior. And then another thing that we started thinking about is some of these brain-inspired mechanisms, looking at the static excitatory inhibitory balance. And what we found was that our reservoirs perform best in regions that are balanced or slightly over-inhibited. And in those regions, we see reduced sensitivity to other hyperparameters. And what do I mean by that? I mean that there's a wider, when I set my global balance to the slightly over inhibited regime, there's a wider range of hyperparameters where I get good performance. And if I'm in the slightly excitatory regime, that range of hyperparameters, I only can find this narrow range where everything seems to work, but it's very fragile. It breaks down quickly. And so then we started thinking about neuron level plasticity mechanisms, driving the reservoir towards these beneficial regimes and improving performance, both in terms of memory capacity and these time series prediction tasks that I mentioned. What we saw is that, well, if I introduce that mechanism, that introduces another parameter in my system where I have this target firing rate for my nodes. But if I introduce heterogeneity in target firing rates, which is also brain inspired, thinking about heterogeneity in neuronal properties and sensitivities, this further reduces our task specific tuning requirements. So we get a more general reservoir. And I just want to mention that I've talked mostly about two papers. So before I talk about some other ongoing work, I've talked mostly about two papers here, and I have the references here, a paper with Chapuri et al., which is about the hybridization, and a paper with Srinivasan and Plens about boosting reservoir computing with brain-inspired adaptive control of EI balance. Now, before I conclude and take questions, I want to tell you a little bit about some other recent ongoing work that I think may be of interest to some of you. So we, in our group, have done a lot of reservoir computing for time series prediction tasks. And we did parallel reservoir computing for spatiotemporal systems in a 2018 paper. And then we followed that doing parallel machine learning for forecasting the dynamics of complex networks. And this is a problem I think might be relevant to some of you. And we think about it in terms of thinking about brain dynamics. Let's say my data is EEG data from different channels measured at different locations. And I know that there's some underlying network of connectivity that the channels are going to be, those measurements are going to influence each other. And so what I can do is break this up. I can have each reservoir predicting just one channel. For instance, this reservoir predicts the dynamics of node 2 in my real network. And but it also gets input from the other nodes or channels in my EEG data example that I think are related to it. And we can build basically this parallel reservoir architecture that is meant to reflect the true architecture of the underlying network system for which I have time series data. And we see good performance whether we know those connections, and when we know the true connections, we get very good performance. But even when we have to infer what those true connections might be, this parallel network, this parallel structure where the reservoir, the connections of the different reservoirs mimics the inferred connections of the true systems gives us really good and strong time series prediction. So another thing we've been doing is tailored forecasting from short time series via meta learning. And in a brain context, you could think about, let's say we have different trained forecasters for different to predict the dynamics of different individuals. And now we just have a short time series for one new individual. We've trained these forecasters on really long time series for some individuals. We have lots of data for them. But now we have just a short amount of data for a new person. We train a meta learning signal mapper to give us the parameters of a new forecaster such that we can learn from just a short signal. We harvest all the information across these forecasters to create a new forecaster model parameters, new reservoir computer for that, for the new person, and create a new forecast. And then we've been thinking about generalization. So this is a kind of generalization. We also think about generalization to unseen state space. So I'm training my reservoir computer, but I only ever see one area of the state space. When does it do well in other areas? So we had a recent paper on that topic. And then we also have an ongoing collaboration with folks from the School of Medicine at Yale, where we're using reservoir computing to build digital twins of the brain dynamics. And so this is just a little sampling of some areas that I thought might be relevant to some of you. So with that, I will end, and I'm happy to take questions.
Thanks so much. That was a wonderful talk. I'm just looking for the clappy emoji. There we are. Lots of other people clapping. Thank you, Michelle.